Welcome. So, if you've ever stared down an unbalanced three-phase electrical set, you know it can honestly look like a mess. Just three completely unrelated phasors pointing in totally random directions. But today, we're going to mathematically deconstruct those chaotic, unbalanced systems into structured, beautifully balanced patterns using symmetrical components. It is absolutely a game changer for gaining a much more useful view of what's actually happening in your system.
Here's our roadmap for this explainer. We'll hit the three sequence signatures, the transformation matrix interface, decomposing a synthetic set, reconstruction and verification, physical context and residuals, and finally wrap up with the six-step readiness loop. All right, part one, the three sequence signatures. Let's get into it.
The foundational concept we have to grasp here is that literally any unbalanced three-phase set can be perfectly represented as the sum of three balanced patterns. And here's the kicker, absolutely nothing is discarded. Zero sequence gives us three equal phasors pointing in the exact same direction. Positive sequence, that's your equal phasors separated by 120 degrees. And then negative sequence is also a beautifully balanced set, but the rotation is totally reversed. Keep in mind, though, these are purely mathematical patterns right now, not immediate identifiers of physical faults. Now, to actually make this math work, convention is everything. Throughout this explainer, our declared positive phase order is ABC. We anchor all of this with the mathematical operator A, which just represents a rotation of positive 120 degrees. Because of that, its square, A squared, gives us a rotation of 240 degrees, which, if you think about it, is mathematically exactly the same as negative 120 degrees. This brilliantly shows that convention in action. When we put the positive sequence right next to the negative sequence, you can see they're both perfectly balanced sets. The fundamental difference between them is entirely in the rotation. It's a simple visual shift, sure, but it has massive implications for our calculations down the line. Moving on to part two, transformation matrix interface. So we need to establish the mechanical interface we use to translate between standard phase quantities and these underlying sequence components. You absolutely must explicitly declare your vectors first. The phase vector has to be explicitly ordered ABC and the sequence vector ordered 0, 1, 2. Then, to reconstruct your phases from those sequence components, you just multiply your sequence vector by the forward transformation matrix. But what if we need to go the other way? To decompose the original phases into sequences, we apply the inverse matrix. And here is where you really need to pay attention. You absolutely must include the critical multiplying factor of 1/3. Let's just pause to lock that in. That 1/3 factor, completely non-negotiable when you're running the inverse transform. Okay, part three, decomposing a synthetic set. Let's put these rules to work and run a highly controlled numerical decomposition. We've got our precise inputs for phase A, B, and C right here in rectangular form. These are our specific phase cards for the operation. Phase A is 98 plus J0 volts. Phase B is negative 52.124 minus J83.603 volts. And phase C is negative 27.876 plus J89.603 volts. Just a classic, complex, unbalanced set. Applying our declared inverse transform, and definitely remembering that 1/3 factor we talked about, yields these exact sequence components. Our zero sequence component resolves super neatly to 6 plus J2 volts. The positive sequence component comes out to 96 minus J8 volts, and the negative sequence component is negative 4 plus J6 volts. Take a close look at those results. Yes, the positive sequence magnitude is clearly the biggest, but those smaller components still matter immensely to the full mathematical picture. That statement is backed completely by the math. However, you've got to remember our strict boundary here. Sequence magnitude alone does not grant operating approval. You absolutely cannot make a claim about the physical cause or the acceptability of the equipment based merely on these sequence magnitudes. Which brings us to part four, reconstruction and verification. Look, a calculation just isn't finished until it's verified. Reconstruction is our definitive acceptance test. By running our new sequence components back through these specific equations, the reconstructed values have to flawlessly match all three original rectangular inputs. Phase A is just the simple sum of V0, V1, and V2. Phase B uses V0 plus A squared times V1 plus A times V2. And phase C, that's V0 plus A times V1 plus A squared times V2. But we definitely don't stop there. We have a second mandatory check for our balance scale. To be absolutely certain, the sum of the three original phase quantities has to exactly equal 3 times the zero sequence component. Passing two distinct checks like this is vastly stronger than just trusting a sequence magnitude because it kind of looks plausible.
Let's pause and appreciate this result. Both sides of our balance scale resolve perfectly to 18 plus J6 volts. Boom. The math is proven and our sequence extraction is officially verified.
Let's dive into part 5, physical context and residuals. Now we have to transition from pure, pristine mathematical verification into actual physical reality. For currents, if the phase current sum equals 3 times the zero sequence current component, we have to ask a really critical question. Where does that physical current actually go? The residual we calculated is just an algebraic fact, but an algebraic fact doesn't magically build a physical grounded connection out in the real world. The crucial takeaway here is that physical reality depends entirely on the specific constraints of your system. That physical return path is totally dictated by the connection type, the grounding method, your exact measurement location, and your current reference direction. You simply cannot assume a physical layout just by looking at mathematical sequences. And man, you have to be incredibly careful with line-to-line voltage measurements. If you subtract one phase voltage from another, equals zero sequence phase terms actively cancel each other out. It mathematically zeroes it out. But this merely means your measurement definition removed those equal terms from your view. It absolutely 100% does not mean that zero sequence is absent from the underlying phase to neutral voltage. Finally, part 6, the 6-step readiness loop. To guarantee absolute mathematical discipline every single time you do this, you need to memorize this precise loop. Step 1, declare your phase and vector orders explicitly. Step 2, test that convention on a known balanced set. It should only give you a positive sequence component. Step 3, do your calculations safely in rectangular form. 4, reconstruct your original phases. 5, check your phase sum against 3 times the zero sequence. And finally, step 6, rigorously bound your conclusions strictly to the evidence you actually have. This explainer gives you the foundational method and those absolutely essential checks. But if you really want to lock this in, the Moonbow Readiness Kit, specifically MRK-003, goes way further. It gives you hands-on diagnostics, guided decomposition challenges, real debugging cases, and an AI coach that uses strict answer protection rules. It's designed to help turn your practice attempts into verified, unshakable evidence that you actually know the stuff cold. I want to leave you with this provocative thought to chew on. You've now seen how to learn the pattern and mathematically prove the transform. But given that strict, unyielding boundary we just talked about between pure algebra and physical reality, how are you going to safely apply these boundaries out in the field? Knowing the math, that's only half the battle. What are you actually ready to do next? Thanks for hanging out with me and keep exploring these incredible systems.